welcome to our classes. So, we will continue today the discussion about the unique reactivities of bent metallocenes. In the last class, if you remember, we have extensively discussed about the basic difference between the parallel and the bent metallocenes, and we discussed about the some basic and unique reactivities of metallocenes, the ferrocenes, which are the first metallocenes, some of the common parallel metallocenes, and then we started the discussion of the unique electronic properties and try to correlate the reactivities of such bent metallocenes. If you remember, in the last class we discussed that how the electron pair, the lone pair present in the bent metallocenes governs the reactivities. So, today we will cover the unique reactivities of the bent metallocenes, and we will try to then understand that how these properties are essentially useful for many important organic transformation and also for in the catalysis for the value added compounds or in polymer industries. So, let us start our discussion. So, this one actually we discussed in the last class. If you remember, I just want to highlight a few basic points which will be helpful in our classes today. So, if you recall the last class, so this is actually in a category of what we will be discussing in the following classes in the catalysis of polymerization. So, this titanium, zirconium, in these bent metallocenes, you see that these are basically D0. Okay, you see that means there is no lone pair, that means there is no electrons in the non-bonding orbitals, and unlikely in molybdenum, the similar analog of the molybdenum, you see that there is a lone pair, and we saw in the last class that how this presence of the lone pairs differentiates the reactivities. As example, if you have a lone pair, it may act as a Lewis base. If it is vacant, it may act as a Lewis acid, like that. So, we discussed in a category wise that how this electronic factor and the number of metal, apart from the metal CP, how many metal ligand bonds are possible, how the electronic factors governs the unique reactivities, etc. So, today what I will do, I will try to give some flavor that how these unique reactivities of some of the selected metallocene compounds are possible, and how interesting it is, and how these are useful for in catalysis chemistry. And actually many bent metallocene compounds, not only the bent metallocene for as a polymerization catalyst, many bent metallocene compounds are very much used for in other domains of organic synthesis or to make the value added compounds, maybe stoichiometric or maybe as catalysts. So, let us see this example. Okay, so this is tantalum. So, this is basically a case of CP2, okay, tantalum, and is R3 category. That means you see that tantalum is in +5 oxidation state. So, this is +5 oxidation state. Okay, and it is 18 electron role, 18 electron valency electrons. It has 18 electron valency electrons. Okay. Now, this compound, you see that as it is a tantalum, it is a +5 oxidation state. That means it is D0. Okay, that means there is no electrons in the non-bonding orbital. Okay. As you see that the CP2 TAS3 as a catalyst. Okay, so which kind of catalysis it is useful. It is actually industrially used for these very useful reactions. As example here, this is the benzene, the normal benzene. Okay, here all are just normal benzene, and if you want to make its deuterated version, okay, so that means it is C6H6 and this is C6D6. Okay, you need this and catalyst. Okay, this catalyst, and you know that what are the applications of the deuterated solvents. These are used for recording NMR spectra. Okay, we normally use CdCl3. We also sometimes use the deuterated benzene, deuterated toluene, deuterated dichloromethane, deuterated DMSO, or the deuterated water according to its solubility. Okay, so how this is very expensive. This one is very expensive. Okay, and you can check the price in online. Okay, and this one you know is quite cheap. Okay, although benzene is in category of carcinogenic chemicals, harmful chemicals, but sometimes you have to use in lab with all the precautions. Fine. So this catalyst is used for transforming the normal benzene to the deuterated benzene. How does it work? Okay, so let's see. Okay, I will discuss the mechanism. So you know that this is a D0 system. So that means now it is a D0 system. So what first step will be the reductive elimination. Okay, because what you have to do, you have to add, you see, to get from the benzene to the deuterated benzene. So what I need to add? I need to add here the normal benzene and C6H6 and the deuterate D2. Okay, now you see it is already D0 system, that is the tantalum 5. So there has to be reductive elimination reactions. So in reductive, if there is a reductive elimination, then what will happen? It will, I am not writing the ring. Okay, so just I am writing the C5, and you have to assume that these are eta 5 Cp. Okay, I am writing in short. Okay, okay. Now if it is reductive elimination, then what will happen? Now you have a, instead of 3 tantalum hydrogen, you have a single tantalum hydrogen bond. So now it will become now tantalum 3 oxidation state, and it is 16 electron system. Fine. Okay. Now what you have to do? You have a C6H6, that is the benzene. Okay. Let's now pH I am writing in this way to understand easily. So what will happen now? Can you guess what will happen? Yes, there will be oxidative addition. Okay, you remember in one class we have discussed the 4 unique reactions in organometallic chemistry, that is the oxidative addition, reductive elimination, then the insertion reaction and elimination reactions. Elimination is mostly beta elimination is very common, sometimes alpha and gamma. Okay, so these 4 reactions, if you see in the catalytic cycles, these 4 reactions is basically operated in a repeated way, sometimes single, sometimes multiple. So you see that this oxidative addition of pH. Okay, so what will happen now? So it will be like, so this is my pH, this is H, and this is H. So you will see again the tantalum converts to tantalum 5. Okay, now Now you see this is a kind of activation of the phenyl benzene. So as I told that during the previous discussion, this oxidative addition is basically the activation of your substrate. Okay, so you see here, so this is a kind of a activation of your C6H6. Now so phenyl benzene is now inserted, reacted with the catalyst. Now you see left over is the D2. How does it react? So now obviously there will be reductive elimination. Reductive elimination. And reductive elimination of what? It is actually the hydrogen. Now you see what will happen. Again tantalum, now Cp, cyclopentadienyl, as I told, is eta 5, and you see that again the phenyl is there. Fine. Now what will be the next step? Any guess? Yes, next step is now react with the deuterium. So this one. Okay. So what will be the reaction then? Yes, obviously the oxidative addition. So this is again my 3 oxidation state. Now this is tantalum, now Cp, Cp, now you have a again phenyl, deuterium and deuterium. Okay, you will see this one. Okay, so this deuterium and this deuterium. Fine. Okay, now next reaction. Okay, what will happen? Next reaction will be obviously similar. Now it is 5 oxidation state. Okay, now reductive elimination. Okay, any idea? Reductive elimination of what? Okay, so this is, you see that it is 18 electron, this 16, then 18 electron, then 16 electron, then 18 electron. So it's basically kind of, you see the settling between 18 and 16. Okay, so now what we'll see, now this is again reductive elimination, and what you are getting? You are getting the PhD. So you see that one hydrogen has been replaced in phenyl ring, in benzene ring is replaced by one deuterium atom. Okay, now what happens? The same, if it is repeated, okay, another 5 times, eventually what you will get? You will get C6D6. It's very easy, no? Is just based on the simple 2 reactions, oxidative addition and reductive elimination, and you are getting the desired deuterated benzene. Okay, so you see how interesting this bent metallocene, lot of examples, lot of applications, even not only in academic scale in laboratory, but also in industries. Okay. So you see that this is really a very fascinating chemistry of the bent tantalum. Okay, and you have to remember that, see, this is D0. Okay, so that means this is D0. Okay, that means it has to be, how will, see, this is how will you predict or propose the mechanism. You have to see it very carefully. Okay, the 3 steps, you have to see it very carefully, the catalyst, that you see the what are the electronic in the first, what you see, you will see the catalyst. Okay, see the structure of catalyst, metal center, ligands, electronic arrangement. Why electronic arrangement? To check what kind of reaction it can undergo. Like for if it is D0, then it cannot undergo the oxidative addition at first. It has to undergo the reductive elimination, okay, and then only there will be two reasons. Okay, you will see here there is a reduction, and then it is actually giving a vacant space. Here you will see, okay, this the coordination number here 3, 3, 6, 7, 8, 9. Now here coordination number here 2 decreasing. So here basically here coordinate vacant, it's creating the vacant sites here, okay, in the 16 electron system. Why? So that it can react with the substrate. Okay, so by electronic factor, electronic arrangement, by the ligand environment and by the metal center, you have to have some idea that what kind of reaction it can undergo, and then you see the substrate, that yes, this substrate whether it will undergo oxidative addition or reductive elimination, then you judge it and then you proceed accordingly. Okay, so I will also show some example where you can propose the mechanism not just by kind of remembering, but by very logical way. Okay, so you have to be that how many electrons, whether it is 18 electron or 16 electrons, you know that 18 electrons are very stable, so it has to undergo the 16 electron system or 14 electron system to participate with the reaction with the substrate. Okay, now after that interesting example of tantalum 5, let's come to the some unique chemistry of the tantalum, but here +3 oxidation state. So one example is this one. Okay, here it is methyl and here is Cp star. Cp star means actually the, so you know that Cp is this one. Okay, so this is Cp minus. And what is Cp star? Cp star is basically the pentamethyl, same, but this is called the Cp star ion. Okay, so is basically pentamethyl version of the cyclopentadienyl anion. Okay, now here you see that this tantalum 3, tantalum 5, the earlier one, that is the tantalum 5, that means D0. Now obviously how many of electrons will be here? So this is actually the D2 system, obviously. So this is the D2 system. Okay, and 16 electron complex, 16 electron valence electron, actually this is, okay, rather is better to say 16 valence electron. Now this one is very interesting. Okay, this tantalum undergoes a very unique reactions. Okay, that's why I thought to show this example. See, we previously I mentioned that in organometallic chemistry the beta elimination is very common. Okay, beta hydride elimination. Okay, beta hydride in bit elimination, beta hydride elimination is very much common. Okay, sometimes beta carbon elimination also possible, but this one is very common. But if you see the alpha H elimination, okay, this is possible but not very common. This is one of the example where you see the alpha elimination. How does it happen? So you tantalum, okay, so you have a now so this is CH2 and this is H, okay, and it undergoes like this kind of interaction. Can you tell what type of interaction it is? It is, yes, this is called the agostic interaction. Okay, we have seen the agostic interaction mostly for the beta hydride agostic interaction, but here we see that this is alpha hydrogen agostic interaction. Okay, very interesting. Fine. So now, so this is basically is now is activation. What does it happen in agostic interaction? Basically, the sigma electron of the CH bond is donated to the tantalum, and on the return back bonding, the electron pairs is now brained to the sigma star orbital of the CH. As a result, this CH bond is becomes weak, and this is called the activation. Okay, and what happened? It undergoes after that oxidative addition. Okay, so this is D2 still. Okay, and okay, now you see what will happen. Now this is Cp star. Okay, and this will undergo the oxidative addition, and here it will be like this one. Okay, so you will see that the oxidative addition of this CH bond. So this is basically the breaks. Okay, and form the tantalum 5 again. Okay, and it becomes D0 system again. Okay, so here you will see that how interesting this chemistry is. Okay, so here you will see that the D2 okay system is undergoing the alpha H interaction. So this is basically, as it has a this electron pair, so this is donated to the sigma star orbital of the CH. This bond is now weak, the CH bond. Okay, this bond is now breaking, undergoes the oxidative addition of CH and forms the again the tantalum hydride complex, which is again D0, and it is 18 electron system, that is the valency electron. Okay, also you will see that is a very common reactions. You have a 16 electron system, so coordinated unsaturated, also electronically unsaturated, so it easily undergoes the reactions ligands like carbon monoxide or phosphines and satisfies the 18 electron configuration. So this is CO, this is methyl, again you will see this is obviously D2 and 18 valency electron. Okay, so this is really interesting and very unique alpha H agostic interaction. Okay, as I am undergoing the alpha H elimination, which is very rare. Okay, not very common. Okay, fine. Now I am I'll be discussing some of the very unique reactions of the Cp2WH2. Okay, that if you remember what will be its electronic how many electrons will be on the non-bonding electrons. So let's Cp2WH2. So if you recall, so it will be in Cp, this is H. Okay, so this is again D2 electron and it is 18 valency electron. Okay, so it has the non-bonding electron pairs as a lone pairs. Okay, so that means it can act as a weak base, Lewis base. Okay, fine, and that's why it is like Cp2WH2 is acts as a Lewis base and form adduct with BF3. So you know that BF3 is a Lewis acid, so it form adduct like WB, W, CP, CP, okay, here hydrogen and BF3. So this is adduct, okay, acid base adduct, simple, fine, okay, fine. More interesting, here you see that this one, okay, this one, if you irradiate with light, and what happened, the reductive elimination of H2, because you know it has D2 system, okay, and 18 electron, so it can undergo easily the reductive elimination and forms the Cp2W, okay. So now here, now it's very interesting, so it is 16 electron system, okay, now initially it was 18 electron system, and this one can undergo a series of very unique and very interesting reactions. As example, it reacts with cyclic ether and undergo the oxidative addition reactions like this way, okay. So if it is oxidative addition, then what will happen? So this one and like this one. So oxidative addition here, this reaction is the oxidative addition. So again it will become the 16 electron 18 electron system, valence electron system. So it's basically, you see that here again CO bond activation is happening, okay, fine. Now another interesting reactions is similarly, if you react with the C6H6, that is the benzene, okay, what you will get? Obviously you will get this one. So again it is oxidative addition reactions of CH bond. So here also again it is 18 valency electron. Very interesting, no? This is very reactive intermediate, that is after this is very highly reactive intermediate, okay, because it's called also transient species. That means you are creating this reactive species by photolysis, okay, fine. Now as it is 16 electrons, it can also undergoes the simple coordination reactions with other ligands like carbon monoxide or PR3, okay, L maybe this one, so it forms the like this one. So it is very common, okay. The most interesting is that this is used for one very interesting reactions, which is if you take the Cp2W, this one, and react with activated acetyl compound, as example CO2Me, CO2Me, okay, both side ester, and it undergoes the okay, so it undergoes insertion reactions of the alkene and in WH bond, and what will happen? You will get like, okay, this is CO2 Me and CO2 Me. Okay, so you will see here how what is happen here, this one. So it undergoes the insertion reactions of the alkene, okay, into WH bond, and it is cis fashion. So it is regio selective cis fashion. Okay, so this you see that how this bent tungsten bent Metallocene compounds, where metal is tungsten and it is D2 system, can undergo various interesting reactions which are not actually possible for the 3D parallel Metallocenes. Okay, and for all these unique reactions, the responsible is the electronic arrangement. Okay, like here it is D2 system and 18 valence electrons. Okay, and this D2 is, you see that is act as a Lewis base, so it has a excess electron as a lone pair and forms the adduct. Not only that, after the reductive elimination, it can undergo the various oxidative addition reactions, basically the bond activation reactions, and you see that it can activate the CH bond, it can activate the CO bond, it can undergo the insertion reactions of the acetylene into WH bond, that is here. Okay, if you remember, we discussed in the classes what are the insertion reactions. So basically insertion is just opposite to the elimination reactions. Okay, so today what we have done, we have discussed some of the unique reactions of some selected bent Metallocene compounds, and in the next class we will be continuing to discuss the unique reactivities of the bent Metallocenes, especially with the special focus on the group 4 metals, as example the titanium and zirconium, and then we will try to understand what unique properties are actually responsible for using as a catalyst in all alpha olefin polymerization reactions. So till then, bye and see you in the next class, where we will be continuing the chemistry of interesting bent Metallocene compounds.